Hi, this is Jonas from WireFlow, and I'm going to present the Lundby Data Logger, which is a distributed and synchronized data logging system. It's a state-of-the-art logger system, an ideal solution for large synchronized logger systems. It supports real-time monitoring and recording of thousands of channels across long distances. It supports high sample rates with a synchronization of better than 1 microsecond. It can easily be distributed over large areas, and we feel that it's a perfect match for power plants, large factory floors, structured measurements, aeronautical applications, and offshore wind farms, where you have great distances, but you still need high sample rates and good time synchronization. It's built on a proven hardware platform. It's based on NI hardware platforms CompactRIO, CompactDAQ, PXI, and FieldDAQ. And time synchronization is based on the time-sensitive network, and that means that we can get good time synchronization over standard Ethernet copper or fiber cables. Locally, Lundby stores data in the TDMS data format, which is the standard format. This means that we can have channels stored in the same file with different data rates, also that we can add properties or metadata for each channels in the same file as the actual data. The main features of Lundby is that it's distributed, both in terms of I/O and computing, to provide flexibility. It's synchronized to provide time accuracy regardless of the distributed nature of the logger system. It's configurable to meet specific needs, scalable to meet future needs. Since it's distributed, it's easy to add a new node to get more data in the system, and this is also possible to do on the live system. It supports local logging to maximize data throughput, meaning that each logger node is responsible for logging the data its hosts. It's also redundant to maximize uptime. As I said, the logger nodes are self-contained, so by that I mean that they contain both I/O and a logger engine that evaluates triggers, perform calculations, and log data to disk continuously. This reduces the load of a central unit and means that we can run independent of other logger nodes in case of a network loss, power outage, or if a logger node just goes down. The I/O for each logger node can also be distributed using Ethernet CDAQ chassis. So why is Lundby distributed? The reason is that we had requirement from our customer with very high channel counts, very high amount of pre-trigger data, and also being able to constantly calculate channels based on the acquired data. And doing a quick calculation for maybe 12 nodes and 60 channels, that is like 57.6 megabytes per second of data being stored to disk, and we need to be able to store about 7 gigabytes of data in RAM just to handle the pre-trigger data. So the distributed system can easily support this, but in order to expand a centralized system, that would not be possible. So the performance in brief for Lundby is that we can support thousands of channels, and the limit is basically how many logger nodes that you have in the system. And obviously, if you add more logger nodes and more channels, once you go to fetch all that data, it will take a longer time, but we support thousands of channels of logging data. We have a time synchronization of better than 1 microsecond thanks to the use of IEEE 802.1 AS, which is the time synchronization part of TSN networking. We support up to 1 megasample per channel, 1 megasample per second per channel, and we also support cross-triggering, meaning that a logger node can trigger another node. And we can support the NI platforms PXI, CompactRIO, CompactDAQ, and FieldDAQ. Time synchronization is, as I said, is based on the time-sensitive network 802.1 AS feature, and it's realized using a master switch that gets an external clock and is configured as an 802.1 AS master. Then each logger node have a slave switch that is configured to distribute the master clock to the slave devices, and that could be another switch or an I/O node. Within the I/O node itself, we get the absolute time from the network, and then we have an internal oscillator for the DAQ tasks. I should say that the DAQ tasks are also time synchronized using phase locking against the network time. That means that all the DAQ tasks and all logger nodes are also time synchronized using the network time from 802.1 AS. On the user interface of Lundby, you can have status monitoring and configuration. So you can monitor individual channels to see how they vary over time. You can also check the status on each logger node to see if the memory, CPU, and buffers are enough for the task that you currently set up on each logger node. We mentioned that we base this system on DAQ from NI. And based on DAQ means that we also are basing it on virtual channels. Currently, we support the virtual channel types current and voltage, but we plan to support the other DAQ-MX channel types like temperature, strain, etc. in the future. We also support calculated channels, and calculated channels are based on the virtual channels. So if you sample the virtual channels, you can from the virtual channels then calculate a number of different types of outputs. And it could be statistical, like minimum, maximum, median, RMS, mean, standard deviation, variance, and spread. Could also be frequency, phase, amplitude, etc. You can define that the calculated channel should be outputting data at the same data rate as the input channels, but it can also be set to be decimated. For example, having a measurement of the frequency of a signal is not necessary to be returned at 10 kilosamples per second. It might be enough with just 100 samples per second. One of the key features of Lundby is the advanced triggering in the system. And the advanced triggering in the system is based on first channel checks. I mean, checking that channels are within a specific region. And then these evaluations are combined in logical blocks and OR. And that combined gives you a trigger state that can be either on or off. And you can re-trigger a system as well, so you can prolong the system. One of the features I mentioned to start with is we have distributed triggers. And distributed triggers means that since we have a distributed logging system with many different logger nodes, so we can define a trigger to be active on several logger nodes. And once the logger node detects that the trigger is active, it can send a software trigger to the other logger nodes. And since we're using this big pre-trigger buffers, it means that the saved data on each logger node will start at the same point in time. And each logger node can have multiple active triggers at the same time, and they're either local or globally triggered. And I should say also that triggers can be defined or added, removed on a live system. There's no need to reboot the system or do anything else to add a new trigger system. I also mentioned in the beginning that we feel that this is a perfect match for example, to power plants. And this is a case study for the data logging at Forsmark nuclear power plant in Sweden. And that is a high channel distributed and synchronized data acquisition system where we have data maybe 100, 200, 300 meters apart, and is based on the Lundby Data Logger system. Thank you for listening.